In this lesson, I'll show you how to solve exact first-order differential equations. This is part 1. The first question reads, solve y dx plus x dy is equal to x dx. The variables, as you can see, are not separated now, and it turns out that there is no amount of manipulation that will separate them like we had in previous lessons, where we had terms dedicated exclusively to one variable. However, the combination of terms, namely y dx plus x dy, is something that is not unfamiliar to us. In fact, let's say we had to find the derivative of the function y is equal to xy. If we were to derive this implicitly, we would end up with dy over dx is equal to, and on the right side we would have to use the product rule where x stays the same and we derive dy. We have dy over dx. Then we take the derivative of x and leave y the way it is. So I'll just leave y the way it is, and taking the derivative of x with respect to itself gives you dx over dx. And usually we just write down 1, but it's really dx over dx. This gives us x dy over dx and plus y. Now if I multiply the left and the right side by dx, I'll end up with dy is equal to, this dx cancels out, and this y becomes dx. So what this tells me is that if I take the derivative of xy, I will end up with the following integrable combination. This then, what I'm highlighting, can be changed with the left side, giving us d bracket xy is equal to x dx. Now I can integrate the left side and the right side. If I integrate the left side, I will get xy. Integrating the right side will give me x squared over 2 plus c. Dividing both sides by x to solve for y gives me y is equal to x over 2 plus c over x. And this represents the answer to question 1. So before we move on to question 2, the expression y dx plus x dy from example 1 is an example of what we refer to as an integrable combination, and a few well-known combinations are shown to the right. With that being said, let's move on to question 2. We have to solve dy over dx is equal to y bracket 1 minus xy over x. So can we manipulate this equation so that it matches one of these well-known combinations? So let's start by expanding the numerator and see what happens. So I'll expand this y to this 1 and to the negative x squared. If I do that, I end up with dy over dx is equal to y minus x, y to the power of 2 over x. Next, what I can do is clear the denominators by multiplying both sides by dx and x. In other words, I can cross multiply at this point. So if I do cross multiply, I will end up with dy times x, so this times this and this times that. Y dx minus xy squared dx. Let's see if this is starting to look like one of our combinations. Nothing so far, although if I move this term over to the left side, I'll end up with the following equation, which looks very similar to this particular combination, where we have y dx minus x dy over y squared. The only difference, though, is that we don't have a y squared at the bottom. So what I can do is divide both sides by negative y squared, and if I do that, this will cancel out with this. Leaving this negative out here, at the bottom we'll have y squared. This negative will influence the sign of this term and make this negative into a positive. Now we have an exact match to this combination. Therefore, I will switch the left side to x over y is equal to x dx on the right side. This integrates to x squared over 2 plus c, and the left side becomes x over y. You can stop right there, or we can solve for y by combining these two first, where we end up with x squared plus 2c over 2 and x over y on the left side. That hasn't changed. Then we reciprocate both sides, and if we do that, we end up with y over x and 2 over x squared plus 2c. Multiplying both sides now by x, this cancels out. And on the right side, we have 2x over x squared plus 2c. And this will represent your final answer. And there you have it. 2 examples on how to solve exact first-order differential equations.